Hey, in today's video, I want to talk about one of my favorite mathematical proofs. This is a proof of the existence of infinitely many primes. We try to accomplish many things with mathematics, and from our work stem many applications. But behind the scenes, some very fascinating things happen. Proofs are one of those things. There's a sense of certainty that comes from a proof. That is, if you accept the premises, which in mathematics can include axioms, then you must accept the conclusions. There is no uncertainty. Full disclosure, there's a little sleight of hand here, because accepting the axioms isn't necessarily a given. Most of the time, in my personal experience at least, the axioms are nothing more than tiny principles that are kind of hard to argue with. But if you do accept these premises, then you can feel exactly as confident in the conclusion as you do about those premises. The proof I'm going to show you today is one of my favorites. One of the secrets that mathematicians know is that there is a beauty to this stuff. And so today, I'm going to try to let you in on that secret. Let's start with understanding the proposition, that is, the statement we're going to try to prove. There are infinitely many primes. Well, okay, but what's a prime? The easy answer is that it's a positive whole number that's evenly divisible by only one and itself. What does it mean to divide evenly? Basically, it means that there is no remainder left over when you perform the division in question. For example, you would say that 12 is evenly divisible by 4, like so. We can also phrase this as 4 divides 12. On the other hand, you wouldn't say that 5 divides 12 because you have a remainder of 2. This can be written as a proper fraction or as a decimal, like so. In the case of a prime number, let's say 7, this happens with every single number you try except 1 and 7. Because no number bigger than 7 is going to work, we only have to consider those numbers less than or equal to 7. And here's what it looks like. By contrast, we would say that 12 is composite. This is its breakdown. It's divisible by a lot of numbers other than 1 and itself, 2, 3, 4, and 6 to be precise. Numbers greater than 1 come in two flavors then, prime or composite. A number can't be both, and it must be one or the other. There's even a neat little result here that bears mentioning. It'll come in handy later. It's called the fundamental theorem of arithmetic. To see what it is, let's take a look at 12. We know that 12 is the product of 4 and 3, so we can break it down like so. This way of writing it says that these two numbers here, when multiplied, give you 12. Now you might have noticed that we can break down 4 in the same way, because 4 is the product of 2 and 2. The notation means the same thing here. 2 times 2 is 4. In fact, you can go all the way up. 2 times 2 times 3 is 12. Now, we might like to go further, but we can't. Both 2's are prime, as is the 3. Sure, you could say that 3 is 3 times 1, but that would render the notation useless, because if you let that be a rule, then you'd have to follow that rule every time, forever. So for practical reasons, let's just not. What we've done is called factoring. That is, we took a composite number, 12, and broke it down into other numbers. Each time we did this, we factored it. We factored 12 into 4 and 3. We factored 4 into 2 and 2. However, you might notice that we kind of hit the bottom, in that every resulting number is a prime number. This means we now have the prime factorization of 12, which is 2 times 2 times 3. It's often written with exponents, so it'll look like this, usually. What's interesting is that I'll bet that half of you watching this said, I would have broken 12 down into 2 and 6. And if you are, you may be wondering if you get the same prime factorization. Turns out we do. Here it is. As it happens, the prime factorization is unique. That is, each composite number has a unique prime factorization, a unique combination of prime numbers that, when multiplied together, give you the composite number. Here's the prime factorization of 100. Put a pin in this. We'll come back to it. Back to the proof. So now we can understand the proposition, which is there are infinitely many primes. Here are the first few, starting with the number 2, which is the first prime number. In proving this proposition, I'm going to be basing my strategy on the method outlined in Euclid's proof of this. As for me, I find it to be the most attractive. It won't be the exact same proof, but it'll have the same spirit. To begin the proof, we observe that this can really only go one of two ways. Either there are infinitely many primes, or there are a finite number of primes. That is, there's a certain number of them and no more. If we can show that the second option is impossible, then we know the first one must be true. So let's show that it's impossible for there to be a finite number of primes by saying, if there was, then we get a contradiction. If there was a finite number of primes, that means we could count them, right? Let's say there's n of them, where n can be any natural number. And with that, we can make a list of all the primes, which looks like this. The little number next to the p is called a subscript. To understand what it's saying, p sub 1 is the first prime, p sub 2 is the second prime, p sub 3 is the third prime, and so on. When we get to the last one, we say that p sub n is the nth prime. We can then write them all out as a list like so, and we've captured all of them. There aren't any prime numbers that aren't on this list. Seems fine, right? Except we can make a new one, sort of. Let's take every single prime and multiply them together. However long it might actually take to calculate such a thing, you can be certain that you'll at least get a number as a result, which we'll call m. I claim that m plus 1 isn't divisible by any primes on the list. Let's see why. Well, surely m is a composite number, right? I mean, we know it's prime factorization. It's literally all the prime numbers multiplied together. Doesn't seem to get much more composite than that. Now, let's say that the number m plus 1, let's call it x, has a prime number on our list that divides it. What that means is that there is a prime number on this list that divides both m and x, which doesn't work. Here's why. Think about 6 and 8. We know that 2 divides both of them, as we can see here. However, 3 only divides 6, not 8. We can see it here. But there's another clue. You see, the difference between 6 and 8 is 2. There's no way to fit a 3 in that difference, so 3 cannot divide 8. There's not enough space. The takeaway? For some prime to be able to divide two different numbers, it must be able to divide the difference as well. So what's the difference between x and m? Well, remember that x is m plus 1. The difference is 1. That means that for some prime on that list to divide both m and x, it must also be able to divide 1. And because the smallest prime is 2, and certainly nothing bigger will fit, no prime will ever fit. And here's the contradiction. This may feel a bit like the ending of Inception. No prime number on our list of all primes divides m plus 1, so m plus 1 is either prime or divisible by primes that aren't on our list. But that means that our list of all primes is incomplete. This means that it was never a list of all primes to begin with. This means that there are not finitely many primes. This means that there are infinitely many primes. Quod erat demonstratum, which is Latin for what was to be demonstrated. Usually mathematicians just say QED. It's kind of like a mathematician's way of saying mic drop. So, to recap, if there are finitely many primes, then we can make a list of them. Make a new number by multiplying everything on the list together and adding 1, and then show that this new number isn't divisible by any number on our list, meaning the list is incomplete, meaning that there aren't finitely many primes, meaning that there's infinitely many primes. Mind blown. There's whole fields of study that this is related to. But I don't want to get into application right now with this because there's something pure about it. Untouched by application, it's not unlike the fresh snow on a winter day. Then again, at the time of recording, it's spring, darn it, and I'm kind of done with snow. There's many things we know and can prove. There's also many things that we don't know and haven't proven yet. What things do you want to try to prove? What questions do you want answered? Post them in the comments below. Thanks to Origami for all their support, and thank you to my patrons for your support as well. I couldn't do this without you. And congratulations to you on reaching the next term in your own Taylor expansion. I'm Derrick Taylor, and I'll see you next time. Thanks for watching. If you like this video, please click like and subscribe. If you really like the video, come on over to our Patreon page where you can get involved and see all the cool stuff we're doing.